Hello, hiya, Kutadana, just you for now, but welcome to this latest lecture in the A Star series. So, what we are going to do today, we're going to have a bit of a look at probability. So, we'll look at some of the general rules with probability and, yeah, a few questions to do with it um, as well. Um, all right. I won't. I assume you've got access if you want it to the YouTube playlist for this series. I'm not going to share it right now. If you do need it, let me know. If not, if other people turn up later, I'll probably share it later on in the class. But as always, I'm going to share on the screen. If you've got any questions at all, anything on your mind, obviously it's just you for now. So do feel free to take advantage of that as well, even though we will go through the lecture as normal, even if it is a just one person class because of the people watching it, the recording on YouTube. And yeah, just to be clear, as always, this lecture is being recorded, but we're going to focus today as said on probability. Okay, and so probability, here's one sec. Welcome Anna as well. And so probability, this is the study of how likely an event is to happen on a scale from impossible to certain. So that's what it represents when we talk about probability. And so you may see a few different types of questions about probability, but that is the main thing you need to understand when it comes to probability. And probability, how it's often shown, is on a probability scale. And in fact, this will happen sort of early in the exam. You might be given a probability scale and you will have to mark the possibility of an event. So I'm going to copy a little probability scale here and explain it. So we've got here, we've got a scale, we've got on the one side, we've got 0, we've got impossible. So basically, when you're over at 0, something just can't happen. So say like the probability of no rain in a year in the UK or something like that is something which just isn't going to happen. It's impossible. It can't happen at all. Whereas likely is something which we count at least statistically certain. For example, the probability that the sun's going to set in the evening, we will mark as certain. So the scale will show everything along those ways. And the further we go towards 0, the more unlikely an event is to happen. The further we go towards 1, the more likely it is that events gonna happen. And so, as you can see here, we got marked on. We have got 1/6, we've got 0.5, we've got 65%. And so you can show probability using fractions, decimals, or percentages. So all of these are acceptable ways to show probability. And often, as we'll see later on, the fraction's the easiest way to do it, but you might get a question where probability, where perhaps it's shown both as a percentage for one thing, as a fraction for another, and so you're going to have to use the conversion skills we have practiced previously in fractions, decimals, and percentages. So we can see a few different things on here. So we can see that like 1/6 equals if an event takes place 6 times, this outcome will happen once. So, for example, e.g. the likelihood of rolling a 6 on a fair six-sided dice, or die if you really want to be technical. But yeah, exactly, the probability of that happening. So that's one way it can happen. There's 6 possible, so we got as a fraction 1/6. So we got here 0.5 equals if an event takes place twice, this outcome will happen half the time. So e.g. a heads on. So if you toss a third coin, the odds of getting heads. And so this could be shown as 0.5. If I was doing my own probability, I'm unlikely to use decimals just because it's a bit fiddlier, but you may come across it in a question. So it's like to say 0.5, hopefully you realise equals a half or equals 50%. All of them mean the same thing. And so finally we got on here, we got it could be shown as a 65%. Well, percentage is out of 100, so really this tells us if an event takes place 100 times, this outcome would take place 65 of them. So e.g. maybe, I'm just making this up, but the odds it rains on any given day in the UK. Well, I'm sure it's higher than that if it's anywhere in the UK, but you get the point. It's something which is more likely than not. And so really the 1/6 is unlikely, to 0.5 is even chance, and I'll just put that word there, and the 65% is likely. So if you got this in the form of a question, you might be asked to mark on. It might, for example, have a spinner, and it will ask you to mark on maybe with an X the possibility of something happening. And then it could be any of these, but it will be something clearly shown and easy enough, hopefully, to work out. Okay, so we'll move on from this in a second. Just give you guys a second to copy it down, and then we will move on to our next thing. In fact, what I'm going to do, I'm just going to give you an example of a question like this, just so you can see it. And normally, if it's just marking on a probability scale, it's going to be very early in an exam. Fairly straightforward. Like as you can see here, this was a question 6 in an older day. So it's a very early draw. So it just says Geeta spins a fair 8-sided spinner on a probability scale. Mark with a cross X. The probability variable land on C. As you can see here, about 4 C's. That's 8 total outcomes. And so half of them are C's. You can see, even if you draw on, half are C's. When it says on the probability scale, mark with an X, the probability that the spinner will land on D. Well, we've only got A's, B's, and C's. There are no D's, so it's impossible. So we're going to mark it with a 0. So you can see that's all it is to it. It's not anything overly complicated. A question like this, it should hopefully be reasonably straightforward to do. But we'll move on from that now. Okay, and so next today, what we're just going to mention quickly, probability notation. I don't think this is particularly important, to be honest, because I'm not sure if, I think if you just write a probability, even without putting a notation like this, you'd still get the mark in the exam. But normally, we write probability in the following form. You'll probably catch me being lazy and not even doing it myself later in the lecture, but it will be like P for probability, X equals, and then whatever it is, so you say here, equals, and then it'll be the probability, whatever it is. And this is where X is the event and prob is the number, so the fraction, decimal, or percentage. So yes, say for example down here, you've got the probability of watching a film tonight is 0.8. So you would just write this as P film, and of course it's not an exact thing you have to put in the brackets, but something like film tonight, film, probably watching a film tonight, whatever you write, and then just equals 0.8. So technically this is how you're meant to write probability. As I say, I would be pretty astonished if you just write 0.8 for an answer and they didn't give you the mark, but it's better to get into good habits just in case. I always think it's better with an examiner. Assume they're going to be incredibly pernickety, incredibly harsh with the marks, and then worst case scenario is still going to get the mark for writing everything accurately. So you might as well do it for that. But then more important than that, we're going to put over here, calculating probabilities. And so that is an equation for calculating probabilities when the chance of all events is equal. And so the way you would do this, you would say, like on the top, you would say ways an event can happen. And then it's going to be over total possible outcomes. And of course, you mentioned already, probability can be shown as a fraction, a decimal, and percentage. And so, if you divide the numerator by the denominator, just like if you turn a fraction to a decimal, you will have the decimal. If you do this and then multiply by 100, you will have the fraction. And then it's a really important thing to note, however, if you do nothing, you already have a fraction. If you write the probability in this form, therefore, you may as well leave your probability as a fraction unless asked to do otherwise. And normally you're not asked to do otherwise. It would just say work out of probabilities. You write it like that. You can. It might say give the probability in its simplest form, in which case you would have to simplify the fraction. But generally, that's all there is to it. So let's give an example of a question down here. CSAG, there are 25 counters in a bag. 17 are red, what is the probability you don't pick a red counter? Well, this again is relatively straightforward, to be honest. There's questions like this with probability, as long as you understand it. I think they'll deny it's quite a nice topic, so you could just say non-red equals 25 minus 17, so equals 8. And so 8 is the real way events can happen. And then our denominator can be 25, because 25 is total possible outcomes, that's 25 counters. And so there you have it, there's nothing else to it. Of course, you could make it a decimal if you really wanted to. You could make it into a percentage, so that should be 32% because we're over 25. But we don't need to do any of that. We can just leave it as a fraction for a relatively straightforward mark. Ooh, right, now something I've neglected to mention up to now, but is a key thing to understand with probability, which will help you out in certain questions, is that probability always adds up to 1 or 100%. So if, as we know, an event has to happen once we have totaled all probabilities, and the technical term for this is exhausted all options. Probability must add up to certainty, which means it will equal 1 plus 100%. Or if it was a fraction, its numerator and its denominator would be in effect the same if you think about it logically, because 7 over 7 equals 1. 3,652 over 3,652 equals 1. If the numerator and denominator are the same, then probability always is going to equal 1. All right. Okay, so let's give an example of a question you could get. I'm going to have to make up the question. Unfortunately, I've lost the question I was looking for. Apologies for that. I'm going to say, e.g., there are only blue counters, red counters, green counters, and yellow counters in a bag. The odds of picking them are shown in the below table. So we've got here, we've got counters, we've got odds, and on the top we've got blue, red, green, and yellow. And on the bottom, we've been given these as decimals. We've got 0.4, 0.35, and 0.12. And so the question is, what are the odds of picking yellow? Okay, so we know when we look at this, we know probability adds up to 1. She's got given decimals here, so we can say 0.4 plus 0.35 plus 0.12 plus y representing yellow equals 1. Now what we got to do, we got to add our like terms, add our numbers together. So 0.4 plus 0.35 plus 0.12. But the easiest way, I know decimals can be a bit intimidating, but just ignore the zeros for now, because if you're doing an effect out of 100, it was 40, 35, and 12, you would get to 75, 87, which means here it is 0.87. So we've got 0.87 plus y equals 1. And now, just like any algebras we've done earlier in the course, we can minus 0.87 from each side to get the y on its own, which means y equals 0.13. And that's our final answer. If we're going to write it out correctly, we should say py equals 0.13. Okay, and you often get a question like that. It might have another stage to it. It might be, but that's 2 at that stage, and so you've got to do additional calculation. But the key thing to recall on something like that is that probability adds up to 1. Okay, so again, I'm just going to give it a second to get all of that down on paper, and then we will move on. What I was saying in general with probability, as you might be able to see from these questions, I think it's one of those topics. If you can put on a little bit of the effort, make sure you understand the basics of it and everything like that, I personally would say it's not a bad topic at all. It's basically something, the rules, I would say, in comparison to other things which might give similar marks, be a similar part of the exam, the rules are not too bad. And two things which get put under probability, essentially this called sample space diagram, but you see it's a two-way table. And so often in the exam, you will be given information which you need to fill out in a two-way table, exactly, or it can be a frequency tree. We're going to look at both, one of both. See, true. The way to do this is to work through the information you are given one stage at a time, as long as you don't rush. It's normally relatively simplistic. So it's normally, as I say, not a bad topic at all. Often these questions will have a directly probability part B. And so I'll give an example here of a two-way table. As I say, it might feel a bit weird to count in probability, but it really comes under that, if anything, within the syllabus. And often these questions will be given a part B. This first one actually didn't have a part B, but I'm going to add one, and then I'm going to show you for a frequency tree as well. So what we've got here, Vadim has 56 clocks. The clocks are only red, only blue, or only black. 32 of the clocks are plastic. 5 of the 14 blue clocks are plastic. 8 of the 12 red clocks are not plastic, and we just need to use this information to complete the two-way table. So this is only a question 9, which means it's not going to give us anything too complicated. Maybe later in the exam they'll make it a bit more fiddly, but the general principles of a question like this is not going to change. So we've got here, what I would always do in a question like this, work through the information one stage at a time. So we've got 32 of the clocks are plastic. Straight away I fill that in, and I can put cross through here because I've dealt with that. We are told 5 of the 14 blue clocks are plastic, so we can put a 5 here, but we can also put a 14 here. To find out non-plastic, we can do 14 minus 5, so we get a 9. So again, we can cross that out. That's been dealt with. And we're told 8 of the 12 red clocks are not plastic. So again, we can put an 8 here, a 12 here, and our plastic is going to be 12 minus 8 equals 4. So now we've used all the information we've been given in a question, but obviously we have still got some gaps along the way. We haven't used all the information we've been given in the question. Very important. We have also been told Vadim has 56 clocks. So we can pop that down here. And now once you've filled in a lot of the gaps, I always think of this as a little bit like a Sudoku or something, but then it becomes obvious the other gaps you've got. Because we know there's 32 plastic clocks. We know 4 are red, we know 5 are blue, so the rest have got to be black. So we've got to do 32 minus the 4 and the 5, so minus 9, and that gives us 23. Then what can we do next? Well, black, we've still got 2 gaps. Not plastic, we've still got 2 gaps. Well, what we can do, we know in total there are 56 clocks. 32 are plastics. We can do 56 minus 32 to get our other one here, which is going to give us 24 not plastic. And now we've got that. The rest takes care of itself. So we've got 8 blue, 8 red, 9 blue. We can add them together to get 17. Minus that from the 24 total here. And we can add a 7. And we've got 23 plastic, 7 non-plastic. So that gives us 30 here. And now if we add our bottom row, it should come to 56. So we've got 30 plus 14 equals 44 plus 12 equals 56. Double checking it to make sure we've got everything right. Now, what you'll often get on a question like this, more directly probability, you could have, for example, B, a plastic clock is chosen at random. What is the probability for clock is red? And so all you've got to do here, you've got to be a bit careful. Always make sure you read these carefully. Sometimes it will say a clock, but here it says a plastic clock is chosen at random, which means we've got total possible outcomes. There are 32 plastic clocks. Then we got red, we know there's 4, so we can just write this as 4 over 32. Now we haven't been asked to simplify on this question, so we don't have to simplify, but if you did have to simplify, you could divide by 4, so you could say or 1 over 8. But if it doesn't tell you to give your answer in the simplest form, there's no need to do that final stage. If you were asked to do that, that's what you would need to do. All right, so again, I am going to give a second there, and then we will move on to the next one. So as I said, beyond a two-way table, you could also be given a frequency tree to fill out. And a frequency tree is basically the same as a two-way table. It's basically like what we've just done, although it looks very different. So we've got a question here. I'm going to make it as big as I can to keep it on a page. But we've got 120 people were at a hockey match. Each person was asked if they wanted to stand or to sit to watch the match. 75 of the people were female, 29 of the males wanted to stand, 30 of the people wanted to sit. Use the information to complete the frequency tree. So it looks very different, but it's just like what we've just done. We fill in the gaps with the information we've got. This is a question 15, so theoretically it would be harder, but it's actually very similar. I always think a frequency tree is quite a nice topic. But we are told 75 of the people were female, so we can fill that in straight away. We are told 29 of the males wanted to stand, so we can fill that in. And we are told 30 of the people wanted to sit, so we can't fill that in quite yet, but we are gonna get there. We got 120 people in total. So next, looking at this, what other information can we fill out? Well, we can see male is going to equal 120, the total, minus the female, which is 75, which is going to give us 45. So we can fill that in here. And now we can say male to sit equals total males minus the males who stand. And so we have got here equals 16. So we can fill in males at 16. Now we can use our female sit because we know 30 people wanted to sit, the total want to sit. We know 16 are male, and so that's going to give us 14. Again, relatively straightforward as it all is. And then finally, we can cross that out. We've used all our information now, but we got final gap we've got here, so we can say female stand. And that's our total females minus the amount who are sitting, and so that's going to give us 61, so we can fill that in. And now you can see part B here, we're told write down the probability that this person is a male who wanted to stand. So one of the 120 people is chosen at random. So this time it's all the people have been chosen, and so this is our denominator. Remember, probably a male who wanted to stand. If we look there, well, there's 29 of them. So that's a final answer, as simple as is 29 over 120. So nothing more to it than that. We haven't been asked to simplify that, as you couldn't simplify anyway, but we haven't been asked to, so we don't need to worry about that. We can just leave things as they are. All right. Now you might see another type of question which looks just like a frequency tree to do probability, but it's a little more to it, and that's a probability tree. Probability tree. So probability tree. So these show the probability for two or more events, one happening after the other. And sometimes you'll see on probability trees, you'll see ones where the second event is affected by the first event. Sometimes it will just be, it won't be at all. So let's give an example. The easiest way to show you this is in the form of a question. And often a probability tree question, it will come at the end of the exam. It will have two parts to it. Part A will in effect be complete the probability tree, as we're going to see here, and part B will be to calculate a probability. Now explain how you calculate probability of events after. But we know at each stage, I'm going to write out notes on the left as I fill this in the right. So at each stage of the probability tree, the probability must add up to 1, because these are all separate events, so they all need to add up to 1 separately. So here we've got Katie completes 2 events at her sports day, hurdles and javelin. Complete the probability tree diagram below showing the probability of her winning each event. So we got our first event here, we got the hurdles, and we're told there's a 0.4 chance she loses. And so we can do the other side. Well, 0.4, just like 4 plus 6 equals 10, 0.4 plus 0.6 equals 1. So we can put that in. And then we got the javelin. I don't know why I'm saying it like that. We got the javelin here. We got a 0.5, but she loses. Well, 0.5 plus 0.5 equals 1. And then we've got the bottom. If she loses the first event, it's obvious it would have affected her confidence. So we've got a higher probability of losing here, 0.6. And then we've got 0.4. So you've got 3 different areas, all of them add up to 1, relatively straightforward, and it's a nice question, as I say, for the end of the exam if you get the part A. Okay. So welcome tests as well. Okay, and so now we've got that, that's the probability in general. Test. I'm just going to pop off your microphone as it's come through, but if you want to ask anything at any point, just as with any of you, do feel free to put it on. It's no problem at all. But at each stage of the probability tree, the probability must add up to 1. Now, the other thing to say is how you calculate. So to calculate the probability of 2 events happening back to back, so first event and then a second event on probability, we multiply the probability of the first event by the probability of the second event. And so, for example, e.g., Katie has a 0.6 chance of winning the hurdles. She has a 0.5 chance of winning the javelin. Therefore, her chance of winning both is 0.6 times 0.5. And so it's like 5 6s are 30. 0.6 times 0.5 equals 0.3. Okay. And so if there are more than one way an event can happen, you work out the probability for each event individually and then add them together. So here we've got calculate for 2b, we've got calculate the probability that Katie wins one event and loses the other. Well, if we follow a probability tree along, there's a couple of ways it could happen, because you could win the first event and lose the second one. And so the odds of that would be 0.6 times 0.5 again, which still equals 0.3. Or alternatively, she could lose her first event, but she can make a comeback and win the second one. So you'd have 0.4 times 0.4, which equals 0.16. By the way, if you have trouble multiplying with decimals, it can be a bit confusing. You can just do it like any multiplication with decimals like shown earlier. So you could take your decimal points out 2 places, do 4 times 4 equals 16, put it back 2 places, and you get to 0.16. So that would leave us with the P of win 1, lose 1 equals, in effect, the 0.3 plus the 0.16, and so equals 0.46. And that's it. If you think about it logically, the odds of winning 2 events concurrently is always going to be less than the odds of winning 1 event. And it might seem strange, but we multiply for that. But if you multiply by less than 1, a number is always going to get smaller. Conversely, if there's 2 different events, the odds of winning 1 or the other is always going to be higher than the odds of winning just 1. So you add together and get a bigger probability. Okay, so just leave that a sec, and then we're going to go off quickly on another little thing worth mentioning. Another skill. To be honest, I'm hesitant to call like skills easy, because anything with maths, it's only easy if you know what to do. So one thing which is easy for one person, it can be difficult for another. But there's 1 or 2 things in probability. But if you practice, if you get on top of, it's generally more straightforward than some of the other topics within maths. And the next one we're going to show, I would say it's not. I don't even really think of it as mathematics, but it comes up in the maths exam, and this is listing outcomes. Listing outcomes. So you may get a question where you need to list all the possible outcomes for an event. This could be through numbers or letters, but the important thing to say, as long as you are systematic, it should be relatively straightforward. And that's because it's literally what it just says. You just have to list the outcomes. You don't have to do anything more than that. So we'll give an example here. So we've got a math student is randomly selecting a 3-digit number containing the digits 1, 5, and 9, and you need to list all possible outcomes of this selection. And so the easiest way to do anything like this is to sort of start with 1 at a time. So first we're going to do our outcomes where 1 can start. So we can have 1, 5, 9, or 1, 9, 5. And then we've exhausted all the possibilities because our second digit can only be 5 or 9. Now we move on to 5, where it can be 5, 1, 9. Sorry, I don't know why I've put a comma in between there. It can be 5, 1, 9, or 5, 9, 1. Nothing else to it. And so we start with 1, we start with 5, and we just do 9, 1, 5, and 9, 5, 1. So that's literally all it's asking you to do in a situation like that, as long as you are systematic with it. It is generally one of those questions you should just be aiming to score full marks on. It should be one of those questions. There's a few topics where you should be happy if you see them come up in the exam. All right, and I'm just going to show one more example of this, just because it could be with letters as well, but how you would do it is exactly the same. So we've got down here, 1 second, I'm just going to make it as big as possible. So we've got Macy is deciding what colour trousers and what colour jumper to wear. Her choices are given below. So we've got trouser colours, black, navy and purple, jumper colours, orange, yellow, white. If she chooses to wear black trousers and a yellow jumper, that would be denoted as BY, and you need to list all other outcomes for Macy's choice of outfit. So here we've got here, you can list them out. Again, in the same way, where it's all, I'm going to get rid of all other because it never says this, list all possible outcomes for Macy's choice of outcomes. So again, you just start with the black ones. So you could go BO, BY, BW. Do the same for the navy. So you've got no NY and NW, and the same for the purple, so PO, PY, and PW. So you can see it's very straightforward. As long as you read the question, as long as you do what is asked for you, you should be hopeful of getting full marks on a question like that. Okay, so we're just gonna look at one or two more questions to finish today. So we're just gonna look at one more probability tree, and you can see here, and hopefully this will be encouraging. This is from an old GCSE, and it is a question number 27. So you can see this is right from the end of an exam, and it is considered, probability trees are considered sort of a level 5 topic. So we got Amanda has three-sided spinners. We've got 1, 2, 3, 1, 2, 3. Amanda spins each spinner once. Complete the probability tree diagram. So we got lands on a 2. Well, we haven't been told what way to write a probability, but remember we can write as a fraction. So that's 1, 2, and 3 possible outcomes as a third. Doesn't land on a 2, that's 2, that's not a 2, and 3 possible outcomes. Spinner B is exactly the same, so you just got to do the same again. 1 third, 2 third, 1 third, 2 third are all places. The probability adding up to 3 thirds or adding up to 1. So that's all that is to it. And then we got work out the probability that spinner A lands on 2 and spinner B does not land on 2. Well, we've only got one route that can happen because our first one has to land on 2. So we can do that. And then our second one doesn't land on 2. So we can say for part B, our probability is 1 third times 2 thirds. And remember to multiply fractions. So easy fractions, you just multiply the numerator. So 1 times 2 equals 2. Multiply the denominators. 3 times 3 equals 9. So it's going to be 2 ninths. 2 ninths. And that's your final answer. By the way, just to show, and actually, yes, in good habits, so you can say P 2, then not 2, just so we can do our notation, equals 2 ninths. But as I say, I'd be astonished if they didn't give you the mark if you just put 2 ninths in that situation. Just to show you here, you're doing everything correct. If we calculate this, we could calculate this all the way through our spinner. So you could do 1 third times 1 third, which gives us 1 ninth. You got 2 thirds times 1 third again, which is 2 ninths. And you got 2 thirds times 2 thirds. Well, 2 times 2 is 4, which is 4 ninths. So if we add all of our probabilities together, we're going to get to 9 ninths because we've got 4, 5, 6, 7, 8, 9 ninths. So all of our probabilities together add up to 1. A good sign that we are doing everything correctly at each stage. Okay, so we've got another question here. We've got in a bag, there are only red counters, blue counters, green counters, and pink counters. They're similar to the question we did earlier. A counter is going to be taken at random from the bag. The table shows the probability of taking a red counter or a blue counter. The probability of taking a green counter is 0.2 more than the probability of taking a pink counter. Complete the table. So what you could do here is we could almost use algebra here. So we could say the probability, we know the probability of taking green is 0.2 more than the probability of taking pink. So pink is less. We could call pink here, we can call it X. And we know green is 0.2 more, so we could call it x plus 0.2. So it's a little trick here so that we have got some algebra we can follow to get to our answer. Now we've done this, we can write everything out because we know probability adds up to 1. So we can say 0.05 plus 0.15 plus 0.2 plus x equals 1. And then we can collect our like terms together. So our numbers, we've got 0.15, 0.05 is 0.2 plus 0.2 equals 0.4 plus 2x equals 1. And then we can use our algebra skill solving equations to get rid of something on one side. You do its opposite. So we've got positive 0.4 here. We're going to take it away. That's going to leave us with 2x equals 0.6. And then finally, we want to find out what 1x is. We can divide this by 2. And so we can say x equals 0.3. What that means, here we can get rid of pink, and it was x, so we can put 0.3. For green, it's 0.3 plus 0.2, so we can just put it as 0.5. I'm just going to write those above just so you've got here what we did. So it's a trick you can do there using applied algebra to solve what looks initially like quite a tricky question. Oh, sorry, Tess, I missed this earlier, but sorry for all of the dramas with your car, but I'm glad it's all fixed. Hope it was not too costly as well. What I'm just going to do as well, Tess, I will, just in case you're missing it, I'm going to share the link to the A-Star playlist. So what I'll try and do, I will get this latest lecture uploaded after class, and then that means if you want to watch it back this evening, you can. If you want to get on with your Friday night and watch it back later, completely understandable. Do it another time as well. But yeah, I will get the lecture uploaded after class. So yeah, if you want to watch it, it's going to be there quickly. All right, then there are 18 counters in the bag, and you need to work out the total number of counters in the bag. So again, this is quite a tricky question in a way because we need to reverse things here. So we know that blue counters equals 0.15. So we know 18 equals 0.15. And so remember, we can turn a decimal into a fraction. So we could say 0.15. The 15 is in the hundredths column. Sorry for the writing there. That's meant to say hundredths. It really just says blah, 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 blah. But yeah, we're meant to say in the hundredths column here. And so that means we can write this equals 15 over 100. And we could simplify that because we can divide the top and bottom by 5. And so equals 3/20. And therefore, if that equals 3/20, remember to get from a part fraction to a whole, you can divide. We want to find out we want to find out 1/20 first. So 0.1, sorry, I should say 18 equals 3/20, and we can divide that by 3, and so it equals 6, 1/20, and then times that by 20 to get to 20/20 equals 6 times 20 equals 120, which is 20/20. So it's a little bit fiddly, this question, probably harder than any of the others we've looked at today for the 2 parts, but we get to our final answer, which is 120 counters. Okay. Now this is actually more like a rule than a question. It's just something I thought of. I didn't see a question, I didn't see the notes today, but it's worth mentioning because I have seen it come up in probability. So one additional rule I'm going to give you just before we finish for today. So in probability, the more data we have, the more reliable the data is. So yeah, say e.g., let's say Amanda rolled just a bias, and if something is biased in probability, it means like it's weighted. So it means it's weighted. So it means it's not the same odds at everything. So tossed a biased coin 20 times. She got heads 13 times. Tatiana tossed the same coin 100 times. She got heads, let's say, 60 times. Tatiana tossed the same coin 100 times. She got heads 60 times. And so we need to say whose results are more reliable to show the bias of the coin, and you need to explain why. So I've seen questions like this come up before, and the answer is just simply that Tatiana's result is more reliable because she has more data. And then, so I should put an A there, and then a part B for this you might be given is use the data to give the most reliable odds of getting a heads possible. Okay, and so to do this, you're just gonna combine the data, because obviously the way to get the most results is just to add them both together. So you would do 13 plus 60 over 20 plus 100, and that's going to tell you equals 73 over 120. And again, it's just the most data we can possibly get, so it's the most reliable the data can be. It's like if they try and work out the probability of something in the modern world, they generally use supercomputers and they will role play a situation billions of times in seconds. It's how they do a lot of predictions, things like that. So it's just the more data you have on something in probability, the more reliable that data will be. All right, well, I'm going to leave it there for today. So thanks a lot to the three of you for giving up your Friday evening. Yep, as I say, I hope your car and everything's resolved test, and I will try to upload this quickly so you can watch it whenever you want and catch up if you wish. But yeah, both of you, hope you have a great weekend, and we will be back next Thursday at 7:15. All right, thank you very much. You too. Bye bye. Bye bye.